Yeah. Welcome to this video where we are going to talk about one of the practical applications of power electronics. As we may have read about some of the basic circuits like buck converter, boost converter, right, choppers, and so on. Yes, those are useful, but if you see a real power electronic circuit or a real power electronic application is much more involved, right? There could be multiple circuits operating at different frequencies. So the overall system is usually much more complex, and yeah, still some of those basic building blocks gets used, but they are packed together in a more complex fashion. So let's start with talking about the LED lights. To make the understanding a little bit simpler, I have this LED panel with me, right? This is a LED light which usually fits into the ceiling, right? So it usually goes into a false ceiling where all this electronics also goes along with it, right? And connects to the false ceiling. So we just see the light coming out of it. This particular one is a 15 watt LED light, 15 watt, and it usually comes in these two separate parts, right? Put it in a single box. Obviously, some of the LED panel lights you would see would be an integrated one. They would have everything in a single box. So then the electronics also gets packed in the same frame. But here it's separate. So let's see what each of them is. So this is your final output light, right? First, maybe let's focus on this light part. There's a connector, so let me just disconnect it so that it becomes easier for me to handle each of them independently. Okay, yeah. So, yeah, this is the input, right? So if you see, this has outside ground and inside is the positive input. And this is the light. Now, usually, if you tear them open, what you would see is that these panel lights would have the LEDs connected on the surface, right, throughout, and all of the LEDs sends light inside, right. And on the one surface you have insulation, so no light can come out. The other surface you have a glass, and even in that glass or fiber you still have multiple layers of it, so that the light actually seems like it's pretty uniform, right, throughout the surface. So when it glows, you cannot make out where the LEDs are actually connected, but they are actually connected on the surface, right. One thing you would understand is these LED dissipates a lot of heat, right. If you remember the initial LED bulbs, and even nowadays, right, a lot of these LED lights fail because of poor heat management. So they dissipate light, I mean they give light plus they dissipate a lot of heat. So usually this is the surface from where heat can actually go out to the environment. Now, if you, let's say, pick up a typical light like this one, and you open it up, what you realize is that there are a total of about 90 LEDs connected on the circumference of this, right? There are about 90 LEDs, 90, and they are grouped in 5, right? So they are grouped in 5. How are they grouped? So let's say there are 1, 2, 3, 4, 5 LEDs here. They would be connected in parallel, right? Something I've drawn here to show you what I'm talking about. So if you see this one, right, there is 1, 2, 3, 4, 5 LEDs. Each LED gets a positive and the negative supply, and each of them is connected in parallel. So in such way, these 5 LEDs connect in parallel, right? And there are 18 such arrangements connected in series, right? So if you see, there are 18 such blocks connected in series, and each block has 5 LEDs in parallel. So roughly about 90 LEDs in total. If you consider each LED to be of forward voltage drop of about 3 volt, then you see that they are in parallel. So the voltage drop of this one block would be 3 volt, and if there are 18 such connected in series, so the forward voltage drop is going to be 18 into 3, which is roughly 54 volts, right? So let's keep that in mind, that it's roughly about 54 volt which is required right? If we assume that each LED is of 3 volt, obviously that can also be slightly vary depending on the current. Then comes the, so all of those connects in series, and the final plus and the minus comes here, which has to be supplied by the power supply, right? You can very well call it switch mode power supply. It's a small switching circuit which goes inside this power supply. Right, so this is the main interest for us as far as this course is concerned. This is the connector which goes and connects to the other connector. And if you see the specifications here, I don't know if it would be visible. Let me try. Okay. They say it's 220 to 240 volts, so it can take anything between 220 and 240. Now this is something which is available in Indian market, so it's therefore rated from 220 to 240. You can very well see the other brands where you would have a universal input voltage starting from 110 or 2 going up to 240, right? Then the input frequency is it's suitable for 50 hertz as well as 60 hertz. Input power factor is 0.9. Right now, so what is this is not a very high power factor, neither it's very poor, it's somewhere in the between, it's 0.9. As we understand, it does not have, it's not a motor, right? It does not have a big inductance. So this power factor is not because of the leading or lagging power factor. This is not that. This is the power factor because of the distortion in the input current, right? In one of the subsequent lectures in this class, we'll talk about defining power factor and how the distortion in the current also plays a role in power factor. So this 0.9 is neither leading nor lagging. It's because of the distortion. Moving on, then it says, so these are the input terminals, by the way, right? Phase and neutral. Moving on, it talks about the output side. It says the output current is 240 milliamp, right? So the output current is 240 milliamps. Now, as you understand, most of the LED drivers would behave as current sources, right? Because their voltages would, because if you pick up any diode, their voltages would change. Even a small change in voltage could lead a very large change in the current, right? That's because the usual IV characteristics of the diode is something like this, right? And therefore, even a small change in voltage could lead to, let me just draw and then I'll show it to you. Yeah, so even a small change in the voltage could lead a large change in the current, and therefore most of the LED drivers are current sources. They are maintaining the output current. So it says the output current is 240 milliampere. I've already told you the structure of LEDs. You can go back, you can calculate how much current each LED takes. Assuming 3 volt voltage drop, you can calculate how much each LED power is also, right? So you would roughly get about 0.14 watt of power for each LED. So these are like small tiny SMD LEDs, right, which seems reasonable. Alright, and it says the output voltage is 57 volt. That implies that it can give output up to 57 volt. It can still work if the voltage is little less. So again, we calculated based on 3 volt about 54 volts or so. So yeah, that sort of roughly fits in well. So our assumption of about 19 LEDs seems reasonable, although feel free to open it up and see it for yourself how many LEDs it has. Sorry, our assumption of 90 LEDs seems reasonable, yeah. The other thing which you would see here is the ambient temperature and the case temperature. It's abbreviated as small ta and small tc, at least on the one which I'm looking at. So what are these parameters? Ambient temperature implies that this power supply can continue to give the mentioned output voltages and currents even if the ambient temperature is 45 degrees Celsius, right? So if the ambient goes to 50, then the inside chip temperature would also go up and it might very well fail. So it is recommended to operate till 45 degree ambient, and the case temperature, which is this case temperature, to be 75 degrees Celsius, right? So case should not go beyond 75 degrees Celsius. If you see, it also clearly mentions on the top, it's a constant current LED driver, right? That implies, that is what we were talking about, that this forces a constant output current without and the voltage gets automatically decided by this output current and the LED characteristics, right? Based on the current and the characteristics, the voltage gets determined. All right, now the question comes that what goes inside this small box, right? That is the question. How does it do it? It takes AC input, it gives DC output, regulated current. What all goes inside this box? Let me use maybe a pen and a paper and show you a little bit more about this. Let's see what goes inside this LED driver. Yeah. So the main job this driver does is it converts an AC power into DC power. This AC power to DC power conversion is usually done in these drivers in two stages, right? So there's an AC to DC block, and then this AC to DC blocks feed into the another block, which is a DC to DC block. And then this, I'm just drawing a single line, but this would actually be two lines. Okay, let me draw both the lines, and even in the inside, then let me draw both the lines, right? So this is roughly the block diagram of this particular one. Now, why did I say it's not that straightforward? Few things to observe. First is this AC power, PAC. If you just multiply the instantaneous AC voltage with the instantaneous values of AC current, what you realize is that this power is not constant. In fact, it is a function of 2 times, it's oscillating. So it's a function of 2 omega t. So if you, in one of the subsequent lectures, as we move along in this course, we will see that power in the AC circuit is not constant, and it actually oscillates at twice the grid frequency. On the other hand, if you see the light, right, if you remember incandescent bulbs, right, those incandescent bulb, the output power also used to fluctuate with the same 100 hertz frequency, but our eyes are not able to perceive it or not able to differentiate, and we would perceive it as a constant light source. But that is not true with LED lights. So LED lights in actual absorbs pure DC power, right? They do not absorb this oscillatory power. They operate on pure DC, and therefore this is the input power. But if you see the output power, it is constant, right? Always constant with respect to the time. So now the question is, how does this driver, right, magically makes this oscillatory power into a constant power? If you see, power has to be, power or energy is always conserved, right? So you can anytime apply the total power input plus total power stored or getting into some other element must be equal. The sum of input plus output plus stored, if you take it with appropriate polarities, must come out to be 0, or in other words, the total input should be equal to the stored energy plus the total output. So therefore this box, this little box here, must have some way of storing the energy, right, whenever the power is positive, and then releasing that energy whenever the input power is negative to the output, right? So this is this function we will see, although it's fairly simple in this box and it is done usually by a capacitor, but we see that there are a lot of interesting options to achieve the same functionality. Right, so this is one challenge. Then the other thing what you would observe is now this rectifier input voltage is about 230 volt. This is usually a diode bridge rectifier, and therefore what you get at the output is the peak of the 230 volt, which is roughly 300 to 325 volt. Now from this 300 to 325 volt, one converts it and generates an output voltage, which as we have seen and which is there in this written in this box, it's about 57 volt nominal. So how does this conversion happen? If you see, can a buck converter do it? So here we are talking about a sort of a gain of 1 upon 6. Right, so we are talking about reducing the voltage by 6 times. Right, what is 1 upon 6? 1 upon 6 is nothing but approximately 57 upon 325. Right, so we are talking about reducing the voltage by 6 times. Again, as we move along in the course, we would see that a buck converter is not a good thing to use if you really want to buck by a large gain. Its efficiency becomes really poor, its device utilization becomes poor, and so on. And therefore, people don't use buck converter here. One would use either a flyback or a forward converter. Forward converter would make more sense because it would not have too much of output ripple, and therefore the current flowing into the LEDs would also be almost constant. So as we saw, it's not most of the power converters, right, in real applications are more complex than what we would study in the beginning lectures. But together, those converters and those concepts can help you really understand, build, analyze, debug, whatever, these more complex circuits. And for example, this one we have just seen that it includes multiple converters. Even this one does a magical job of avoiding the oscillatory power from the AC circuit to flow in the DC circuit, right? And it also controls the output current and does not allow any ripple, anything to go in the light, right? So, and plus obviously it manages the heat, it dissipates the heat and keeps the devices inside it cool. So this is usually the case with most of the application. They are complex and they require multiple knowledge on multiple subjects to really understand what goes completely inside this one. So that is what we will try to do as we move along in this course. Try to learn each of the module slowly, and then so that at the end you would have the understanding of the overall system and you can analyze power converter system itself.